Pull the air filter off an older engine and you find a small metal chamber bolted to the top. No computer, no sensors, just shaped passages and a few moving parts. This is a carburetor, and for almost 100 years it quietly solved one hard problem on every drive. How does it blend plain air and liquid gasoline into the exact mist an engine can actually burn? Let's slice one open and follow the air through it. An engine cannot burn liquid gasoline. It burns vapor mixed with air in a careful ratio, roughly 14 parts air to 1 part fuel by weight. Too much fuel and the engine floods and chokes. Too little and it stumbles and runs hot. The carburetor sits between the outside air and the engine, and its whole job is to meter that blend automatically, thousands of times a minute, using nothing but moving air to guide how much fuel goes in. Air rushes into the carburetor on its way to the engine, pulled down by the pistons below. Partway through, the passage pinches into a waist, a smooth narrowing called a venturi. The same amount of air must still get through, so where the tube gets tighter, the air has to speed up. Picture a wide river squeezing into a narrow gorge. The water there runs fast and hard. The air does exactly the same thing as it threads the waist. Here is the quiet trick at the heart of it. When air speeds up, its pressure drops. Fast-moving air pushes outward less than slow air does. So inside that narrow waist, a pocket of low pressure forms, weaker than the still air around it. Nothing is really sucking. The outside air is simply pushing harder than the rushing air inside the waist. That small difference in pressure is the lever the whole carburetor pulls on, over and over. A tiny tube opens right at that low-pressure waist. Its other end sits in a small reservoir of gasoline. Outside, air presses down on that fuel with normal pressure, but the air at the venturi presses less. So the fuel is pushed up the tube and out into the fast stream, with no pump at all. The harder the engine breathes, the faster the air, the lower the pressure, and the more fuel it draws. The mixture balances itself. For that to work, the fuel must wait at a steady level, never too high or too low. Beside the venturi sits a small chamber called the float bowl. A hollow float rides on the surface like a tiny buoy. As fuel feeds in, the float rises, and a needle valve closes off the supply. As the engine drinks the fuel down, the float drops and the valve opens again. It holds one calm, constant level for the tube to sip from. Fuel leaving the tube does not stay a stream for long. It meets air moving far faster than itself, and the shear tears it apart, the way wind shreds the crest off a wave. The droplets break smaller and smaller until the fuel becomes a fine fog, almost a vapor, scattered evenly through the air. Spread this finely, it can catch fire in an instant. A puddle of gasoline barely burns. A mist of it, mixed with air, explodes. How fast you go depends on how much of this mixture reaches the engine. That is the throttle, a flat round plate hinged across the passage below the venturi. Your foot, through a cable, tilts that plate. Nearly closed, it almost seals the tube and only a trickle gets through. Tilted open, the passage clears and air pours down freely, dragging more fuel along with it. The pedal does not add fuel directly, it just opens a door for air. At a stoplight, the throttle plate is almost shut, and the air through the venturi is too slow to pull any fuel. The engine would simply die, so the carburetor keeps a second hidden passage, a narrow idle circuit that draws fuel from below the closed plate, where a strong vacuum still lingers. It feeds just enough to keep the engine ticking over. As you open the throttle, the main venturi takes back over, and the idle passage quietly fades away. A cold engine needs extra fuel, because in the chill, some of the gasoline clings to the cold metal instead of vaporizing. So a second plate, the choke, sits above the venturi. On a cold start, it swings nearly shut, throttling the incoming air. With less air but the same fuel draw, the mixture turns rich, heavy with gasoline. As the engine warms, the choke eases open on its own, and the blend thins back toward normal again. Stamp the pedal and the throttle flies open, and for a heartbeat the air surges ahead of the fuel, leaving the mixture too thin to fire well. The engine hesitates. To cover that gap, the carburetor adds a small plunger, the accelerator pump. Linked to the throttle, it squirts a quick shot of raw fuel straight into the stream the instant you press down. That little squirt fills the lean moment, and the engine leaps forward cleanly instead of stumbling. For decades, this dance of air and pressure ran nearly every car on the road. But it could only guess. It could not truly know the air temperature, the altitude, or the engine's mood from moment to moment. Fuel injection, with sensors and a small computer, meters fuel far more precisely and wastes far less. So the carburetor slowly retired, yet the physics it leaned on never went away. It still hums under older engines and small motors today. So follow the air one more time. It rushes in and squeezes through the venturi, where it speeds up and its pressure drops. That low pressure draws fuel up from the steady float bowl, and the fast air shreds it into a fine mist. The throttle plate decides how much of that mixture reaches the engine. While the idle circuit keeps it alive at rest, the choke enriches a cold start, and the accelerator pump covers a sudden stab of the pedal. No computer, no code, just shaped metal and the simple truth that fast air pushes softly. That was enough to carry us down the road for a century. Look closer at the ordinary, and it turns out to be quietly extraordinary.